Hi there, we are EPFL Xplore, a student association and make project from the Swiss Federal Institute of Technology, EPFL. This year, we are proud to present to you our latest planetary rover, which we will present to the European Rover Challenge 2023, Project Kirby. Our objective at Xplore is to combine space robotics with project-based learning. In this endeavor, we have developed a vehicle capable of autonomous navigation, conducting diverse scientific experiments on terrain soil samples, performing precise object manipulation using a robotic arm, and designing a drone to help us in our scientific mission. This project is made possible thanks to our wonderful team consisting of 48 students from diverse backgrounds, each contributing to a specific aspect of the project. In terms of organizational structure, the managing team consists of the president, project manager, CFO, and 5 systems engineers who oversee the mechanical, software, and electrical aspects of the project from a high level. The technical team further divides into 7 subsystems: control station, science, electronics, navigation, handling device, structure, and drone. Since the creation of Xplore, we have consistently participated at the ERC. In 2021, we achieved 3rd place and best prize in science and probing and collection tasks. The following year, we secured the 2nd place and best prize in navigation. Our journey to Kielce has always been filled with excitement as we met like-minded individuals and strive to achieve excellence. This year is no exception. Since last September, we have worked on increasing our rover's robustness and developing systems that will enhance our scientific discovery capabilities. With its 4 steerable wheels, differential system, and increased suspension robustness, Kirby can traverse rough and uneven terrain with ease. The wheels are coated with polyurethane, which increases the rover's grip on steep slopes and prevents any slippage. The rover's differential bar ensures stability during uneven terrain traversal, while the service module protects our custom-made electronics and power supply module from harsh weather conditions. Kirby can move forwards and backwards, turn on itself, and drive on inclines up to 20 degrees. We can control the rover manually by receiving video feed from 4 cameras attached to the rover's chassis and 2 located on the handling device. Autonomous navigation is made possible thanks to our LiDAR and stereo camera. By merging data from these sensors, we can reconstruct a 3D point cloud of the environment and use this to generate a cost map of the terrain. The addition of the stereo camera this year gives us a denser point cloud, which in turn improves obstacle detection and makes the rover's traversal more secure. If any form of danger threatens the rover, an accessible red emergency button can be pressed at all times. This will cut the power from the battery to the rest of the system and stop the rover's movement immediately.
Kirby's handling device is crucial to completing the maintenance and scientific tasks. Its 6 joints provide flexibility in manipulating small elements on a control panel in direct and inverse kinematics. A voltmeter is attached to the arm's end effector, allowing us to measure the control panel's voltage during the maintenance task. The handling device is also equipped with a raster device inspired by NASA's mining robot. Rotating the raster in the soil will allow the rover to perform sampling of regolith. Once the surface sample is acquired, it is dispatched in a container located at the back of the rover, where samples can be weighted. This year, we aim to perform the maintenance task autonomously. By using a depth camera attached to the gripper to detect AR tags on the control panel, we can acquire knowledge on their position and perform path planning. This year, the science team faces a new challenge, collecting a deep sample at a minimum depth of 30 centimeters and with a mass of 100 grams. To accomplish this mission, we designed a 2 degrees of freedom drill powered by 3 DC motors. These include 2 actuators for linearly ascending and descending the first and second stages, and another actuator to operate the drill's auger in rotation. The first linear stage encompasses the support module responsible for holding the container and conducting the science experiments. Its objective is to reach the ground to facilitate the drilling operations. The second linear stage, known as the motor block unit, allows the drill to reach this 30 centimeter depth mark by simultaneously rotating the auger and translating it downwards. Our student-made drone Broccoli will lift off from the rover during the science task, take a high-resolution picture of the Mars yard for interesting objects observation, before landing back on the rover. This year, our science plan is dedicated to understanding the soil's fertility and assessing the potential for farming on Mars, taking space exploration to new frontiers. This crucial step paves the way for the establishment of durable human colonies on the Red Planet. To carry out this ambitious plan, we rely on 2 multitask sensors and 1 spectroscopy sensor. The 2 multitask sensors allow us to collect data on the soil's nutrient concentration, such as nitrogen and phosphorus, along with the local soil temperature and humidity. The spectroscopy sensor is located within the science experiments module. By emitting light at different wavelengths, this sensor captures the refracted light from the soil. Composition is identified by comparing the light spectra to a library of known spectra related to a material. Finally, a rock will be collected during the science task. We have designed a simple and large collection container to allow the robotic arm to deposit the selected rock and weigh it in situ.